So hello everyone, today we're gonna talk about the Lagrange multiplier. Okay, let me erase this stuff. You guys shouldn't be seeing this at the start of the video. Okay, so Lagrange multiplier is a really genius idea when it comes to computing the maximum value of the intersections between two 3D surfaces. Okay, if you think that's a little bit too abstract, here are two here's the visualization of these two 3D surfaces. Okay, so the first thing, oh shoot, no. The first thing to understand here is this graph. Okay, it's called contour line, but it's just a way to visualize the cross section of the two graph. Okay, so now we're just gonna call the cylindrical graph as H, as SG, okay, SG, and this one as F. As you can see, okay, so K1, K2, and K3 are just three constants. They are the possible value for Z, which means you can see the cross section of the same function of the same 3D surface at different Z value, which means at different height. As for contour line has its own special rules. The differences in height between any two contour lines are the same, which means K3 minus K2 is equal to, oh no, K3 minus K2 is equal to K2 minus K1. The same thing, the same thing. So as you can see here, um, when a K is really small, which means the Z is really small, the cross section of the G graph completely includes the F graph at the minimum point here, However, at the maximum point here, the F graph completely include the G graph, or should I say the cross section, at that point, the cross section at a level of the F graph completely includes the cross section of G graph at the same Z level. So it's actually okay. It completely includes it. However, they have 2 points intersected, uh, which is the one that we're looking for here. So after understanding the graph, we can get to some math stuff. Okay, so the first thing we need to understand here, the first important concept here is the dot product. The dot product is u dot v is equal to the value of u times the value of v times cosine theta. Okay, the whole expression is only equal to 0 when the angle between these two vectors is 0. And then we need to bring up another concept. Okay, so here we have a parametric equation. Parametric equation here is that xt yt. So what it actually means here is that these two functions are actually the same. They are all talking about the circle, which has the radius of c. Okay, so this is a multivariable function. So we can take as different directional. We can take these different directional derivatives. Okay, when we take it with respect to x, it gives us and when it's taken derivative with respect to y. Oh shoot. Should be D. It should be D. It should be D here. However, since it's a circle and has a radius of C, the derivative, okay, no. Actually, so the sum of these two directional derivatives here should be zero. However, this expression is actually a dot product. Surprise! So it's the dot product of u equal to um, over x and v equal to dx over dt dy over dt. Okay, great. Which means they have the dot product of 0, so they are perpendicular to each other. As for a circle, this is where the parametric equation points. However, this is gradient vector. That is amazing, right? I know it is amazing. It is kind of weird to think about. It has a vector that points perpendicular to the actual derivative. Okay, so how does this help us solving this problem? What we're looking here is two circles. Okay, so these rules, I want to have a generalization here. So this rules doesn't only apply to a circle, applies to any closed segments on the 2D surfaces. Like these two surfaces, these two segments, these two closed segments, great. The gradient vectors is always going to point perpendicular to the actual derivative, okay? To the derivative of the parametric equation, or however you put it. This is a gradient vector. Okay, so let's go back to the two circles here. The one circle and one ellipse here. They have the same tangent line, and they are all closed segments on a 2D surface. So they have so their gradient vectors are actually parallel to each other. This helps us a lot. It actually a lot. So, okay, now we're getting to the most interesting part of the whole video. Now we know that they're pointing in the same direction, but how do we write it in a system of equation here? Okay, oh shoot, is equal to lambda g sub x. So the lambda here is just a constant. You don't need to worry about it. Don't freak out about lambda. It's just a constant. If they have the same value in every direction, that means they have the same gradient. Their gradient vectors are also pointing in the same direction. And now, the second part of this system of equation, we have to add a constraint here. What's the radius of the inner circle? If we're not given with a radius of the inner circle, it would be virtually impossible to actually solve this problem. It would be a set. Okay, the answer would be a set. However, okay, x squared plus y squared is equal to c. Okay, then we have a fairly tedious solution here. Okay, the tedious process here. Okay, this would just be at least I know this is 0, right? This will be 2y, and this will be 2x, and this will be let me see, 4x, and this will be 8y. And, this cancel out because they are all 0. And at this point, plugging all possible values into these equations and get a set of points. Okay, AB, maybe negative AB. Oh, yeah, that's 2 points here, right there. Here is their maximum value. It's a pretty long video, and I think I demonstrate this problem fairly clearly, right? Maybe? Okay, just plug in the value and solve for a system of equation, which a 6-year-old can do. Okay, great. Thank you so much for viewing this video. If you can make it to here, you really love math, or you can really endure with bad English, okay? So I know there are a lot of filler words in this video because English is not my native language. But anyways, thank you so much for viewing. But if possible, I'll set for a subscriber. That would be great. And if you think it's helpful, please click the like and leave a comment below that about further suggestions. Oh, thank you so much.